Hello, and thanks for using TickBoom. In this question, we're being asked to prove that a to the power of n plus 1 minus b to the power of n plus 1 divided by a minus b. We want to prove that that is less than n plus 1 times a to the power of n, where b is greater than or equal to 0 and a is greater than b, and we're dealing with n being a positive integer. So, where to begin on a question like this? Now, to prove something like this, often you need to make use of other truths. So, other identities that then you can then make use of. And in our case, the identity that we need to make use of is that we know that a to the power of n minus b to the power of n, that in general is equal to a minus b times the total from I is equal to 1 to n of a to the n minus I times b to the I minus 1. So what we're going to do is take that as a given, but given most people don't actually know that off by heart, I'll show this later. It is possible to prove that this is true, but what we're going to do to start with is just take this as a given and make use of this in then proving what we want to prove. And then on the basis that we can then show that what we've assumed is also true, then our ultimate proof will be valid. So if we can take this as a starting point, this formula for a to the n minus b to the n, then because we're really concerned with a to the n plus 1 minus b to the n plus 1, we can just restate this, replacing all of the n's with n plus 1. So what we'll get is a to the n plus 1 minus b to the n plus 1 is equal to a minus b times the sum from I is equal to 1 to n plus 1 this time. A to the n plus 1 minus I times b to the I minus 1. So all I've done there is taken our general result and inserted n plus 1. Now what I'll do is divide both sides by a minus b so that we can get to the thing that we're trying to prove. So we'll go a to the n plus 1 minus b to the n plus 1 on a minus b is equal to a minus b on a minus b times the sum from I equals 1 to n plus 1 of a to the n plus 1 minus I times b to the I minus 1. And right away we see that these cancel out, so that really what we're dealing with is simply the sum from I is equal to 1 to n plus 1 of a to the n plus 1 minus I times b to the I minus 1. So we've made some good progress here. We've got our left-hand side being equal to something that could prove to be quite useful. But notice we're dealing with an inequality here. So the next thing we need to think about is how can we convert this equal sign into an inequality? And the way we can do that is to make use of what we're told, which is that b is less than a. So if in what we've got right now, I replace b with a, then suddenly I can use my inequality because I can know for sure that replacing b with a will mean whatever I end up with will be greater than what was there before. So we can then say less than the sum from I equals 1 to n plus 1 of a to the n plus 1 minus I times a to the I minus 1. I've just replaced this with a. So where these two things were equal, what I've now written must be greater than what I had before. So that's why I've used this inequality. So now let's simplify this a bit. which will be less than the total from I equals 1 to n plus 1 of A, and I can bring these powers together, n plus 1 minus I plus I minus 1. The two i's will cancel, the 1 minus 1 will cancel, and that leaves us with the sum of I equals 1 to n plus 1 of A to the n. Now notice in our equation here now, there's no longer an I in our series, the things that we're adding up. So fundamentally, we're just taking A to the n and adding it up n plus 1 times. So that's effectively n plus 1 times A to the n, which is what we had in our inequality that we had to prove. So there, by taking advantage of this particular result, I've then been able to prove the inequality that we've been asked to prove. So now what we need to focus on is how can we show that this result is true. Now, in the context of an exam, if you could memorize this, you'd probably get away with starting from that point and not having to show it. But if you weren't familiar with this result, then you'd have the much harder task of having to really start from scratch and having to actually prove this result in order to get to this ultimate proof. So what I'll do now is, just in case you're not familiar with this result, I will show it for you, and then it's something that you would want to add to your toolkit, just add to your repertoire of knowledge, so that when you are facing these kind of proofs, it's just another part of your arsenal that you can pull out and hopefully make use of. So if I just come to a new page, what we want to do is we want to show that A to the n minus B to the n is equal to A minus B times the sum from I is equal to 1 to n of A to the n minus I times B to the I minus 1. That is what we relied upon when starting off our proof. So now let's just hone in on that and try and prove that. Now ultimately, to be able to demonstrate this, you need to be familiar with what's called a geometric progression, or in other words, a series of numbers where the next number in the series is the prior number multiplied by something. So if we look at the series 1 plus x squared all the way up to x to the n minus 1, that's a geometric progression where the first item in the series is the number 1, and the common ratio, as we call it, the thing that we're always multiplying by to get to the next item, is equal to x. Because if we start with 1, 1 times x is x times x is x squared, and so on. So that's the common thing that we're multiplying by. Now with geometric progressions, what you need to have learned or be familiar with is that the sum of a GP is equal to A1, 1 minus r to the n on 1 minus r. And that's something that you wouldn't be trying to prove in this context. You would definitely take that as a given. So in our case, what we can say is our series that is equal to, if we insert our values for A1 and R, A1 is just 1 times anything is whatever you're multiplying by, so we get left with 1 minus x to the n on 1 minus x. And what I'll do is I'll rearrange for this 1 minus x to the n, so we'll get 1 minus x to the n is equal to 1 minus x times 1 plus x squared plus x to the n minus 1. So this now is what we're going to use as the basis for proving the result that we relied upon for our ultimate proof. And the way we can get there is we can let x equal to b on a, and then simply insert b on a into what we've just demonstrated using geometric progressions. So what we'll get is we'll get 1 minus b on a to the n equals 1 minus b on a times 1 plus b on a plus b on a squared plus b on a to the n minus 1. So all I've done so far is just insert b on a wherever there was an x. Now what we'll do is try and simplify this to get to what we're ultimately trying to show. So we'll start by saying 1 minus, and we can expand the exponent, so we get b to the n on a to the n equals 1 minus b on a times 1 plus b on a plus b squared on a squared plus b to the n minus 1 on a to the n minus 1. What will also be helpful is if we bring a common denominator here, so we'll say a to the n minus b to the n on a to the n. And that's helpful because we know we're ultimately going for a to the n minus b to the n is equal to a minus b on a, that's also equivalent, times 1 on b on a, 1 plus b on a, b squared on a squared, all the way up to b to the n minus 1 on a to the n minus 1. Alright, now what I'll do is I'll bring this a to the n over to the right hand side so that we've honed in on what we're looking for. So we'll get a to the n minus b to the n is equal to a to the n times a minus b on a times 1 plus b on a plus b squared on a squared plus b to the n minus 1 on a to the n minus 1. Now what I can do is this a to the n divided by a, this is effectively a to the minus 1, so we can bring those together. We'll get a to the n minus 1, a minus b, 1 plus b on a plus b squared on a squared, and so on. And now what we can do is we'll bring this a minus b out to the front, and we can multiply in this a to the n minus 1 into all these terms, and then bring all these a's on the denominator up and just multiply them by -1. So what we'll get a to the n minus 1 plus b times a to the n minus 1 minus 1 again would be a to the n minus 2 plus b squared times a to the n minus 1 minus 2 would be n minus 3 plus b to the n minus 1, and these two would cancel, so that's all we'd get. And we're very close now. We can write a minus b, and then we can actually write this in the notation that we're looking for. If I write a to the n minus I times b to the I minus 1, we see that that is equivalent to what we had in the brackets here. So for example, when I is equal to 1, we get a to the n minus 1 times b to the 1 minus 1, or 0. So just a to the n minus 1. When I is equal to 2, we get a to the n minus 2 times b to the 2 minus 1, which is b times a to the n minus 2. When I is equal to 2, we get a to the, when I is equal to 3, we get a to the n minus 3b squared, which is that, all the way up to I is equal to n, a to the n minus n, or a to the naught, or 1, times b to the n minus 1. Perfect. So there, using the series, a geometric progression, we've been able to demonstrate what we relied upon for the beginning of our proof, this result for a to the n minus b to the n being this. So now that we're confident that that is correct, then coming back to our original proof, relying on that made this a fairly easy thing to demonstrate. So again, I'll reiterate, this is actually quite a challenging proof if you didn't know this result. If you weren't familiar with this as being something you could rely upon, you'd almost get stuck. You might try induction, but even there, I don't know if you'd struggle to demonstrate this using induction. It probably is possible, but may also be challenging when you get to the step where you have to prove that you'll assume that it's true for n equals k. That'll all be fine up to that step. But then trying to prove that it's also true for n equals k minus k plus 1, that's where you may find that you still need to rely on this knowledge. So definitely quite a difficult proof. I can see why you would have gotten stuck on this question. But a very good example of where you actually need to build up a bit of a toolkit of knowledge of various solutions or mathematical truths that you can then make use of when trying to prove more complex things. So hopefully you found that helpful, and tick boom.